Am I audible? Please just confirm. And the screen is visible or not? You can write in the chat box whether I am audible or not. Okay, thank you. So let us start. So today we are going to solve the week 11 assignment. So actually I have the three assignment, week 20 or your year 2025, year 2024 and 2023. So let us start with the 2025, the recent one. So the first question is about, and today is about the CFD, computational fluid dynamics, week 11. So the first question is, question number 1, CFD provide result of option A, continuous time varying result at discrete location. Option B, discrete point of space and time. Option C, continuous spatial result at discrete time points. Option D, continuous in time and space. So you have four options. And very basic and fundamental question about the CFD. So please just write your answer in the chat box. Which option may be correct? So everyone, please just read the question very carefully and try to understand the meaning of discrete and space and time. So based on your understanding whatever you have learned on the week 11, so you just try to write your answer in the chat box which option may be correct for question number 1. So very interesting question. Okay, so Bala is telling B option, discrete point and discrete points of space and time. Okay, fine. Other student, please also based on your understanding of week 11, you just try to recall your concept, whatever you have learned, and try to write uh, your answer in the chat box. Which option? Bala is telling B option. Okay. Other student, please also try. If you not know, you can just Google. If you not know, first try to recall. If you are unable to recall, then you can Google. No issue. Because here we are doing some the discussion kind of thing, not the exam and the teaching things. Okay, so I'll wait 1 minute more. If not, then I'll explain you in detail what is CFD. So very fundamentally, I'll explain within 5 minutes what is CFD, how it works. So I'll wait 1 minute. Okay, so let me just explain you. So actually in the CFD, what let us suppose you want to solve some pipe flow problems. Any kind of problem, flow problem you can solve using the CFD. Pipe flow, or you can solve the open channel problem also. Open channel with hum, like that. So pipe flow you can solve with different fluids, fluid F1, F2, how varies. So means CFD means is nothing but the set of equations. Remember please, CFD is a very fashionable name, means you are going to solve some set of equation which is your continuity equation and your Navier-Stokes equation. So that's all. But for solving this equation you need the, because before your Navier-Stokes equation is a partial differential equation, so you have to convert, because when you are going to solve some equation for flow problems, so it is very complex problem, so you need to discretize means you need to convert your partial differential equation in some polynomial equations using the different methods are there. So we have the question about it also, so that time I'll discuss what are the methods. And that equation whatever you will convert partial differential equation, that equation you need to solve with numerical modeling or numerical techniques, as you have learned in your, I think, in your the third semester or maybe the fourth semester, you will learn about the numerical techniques, Newton-Raphson method, Runge-Kutta method, Euler method, everything you will learn if you not know. So numerical method will apply for solving that equations. So that's all about the CFD, very fundamental. So you need to solve these two equation by discretized equation, then but discretizing equation you need to solve using some numerical method. But the the complex thing about the Navier-Stokes equation, as we have discussed, this is Navier-Stokes equation is your what is your uh, that is means Navier-Stokes equation you cannot actually very complex to solve analytically, or the second order partial differential equation. So actually the solution for the your complex problem like open channel flow and pipe flow with the different setups, it is very difficult. So what we do, the Navier-Stokes equation convert in the Reynolds averaged Navier-Stokes equation. Again, for solving Reynolds average Navier-Stokes equation, we need some other set of equations, that is your turbulence modeling. So turbulence model we need. So for solving these two equations, how the flow goes, continuity equation, Navier-Stokes equation, then Navier-Stokes equation will convert in the Reynolds average Navier-Stokes equation, then the RANS need turbulence model, then this all the things you will discretize in the forms of your algebraic equation, and then you will solve using some numerical methods. So these are the process. Now for solving this, what you will do, you will divide this domain in lot of small size cell. You will divide, because ultimately you are going to solve what, you are going to solve equation, nothing, you are going to solve some mathematics equation. So for solving mathematics equation, what you will do, you will solve at this location first your equation, then using this data you will move further away, move this side, move this side, you will move further away like that. So remember please, so like that you will move. So nothing in the domain whatever you will define domain means you are going to discretize, you are going to convert your domain in small part, that is meshing. We know this is meshing or gridding or discretization of your domain. So these are the things. So now what you will do, what you are doing, you are discretizing, you are discretizing the domain and in space and time. Definitely in space and time, if you are discretizing in this direction, this is another space, this is another, this is another. So in space also you are varying. Time, when you will run this, what will happen? You will run for let us suppose 100 seconds. So you will see your result, let's suppose after 10 seconds what is happening, after 20 seconds what is happening, when your the equations or this model going to stabilize. So that are things. So here option B is correct. Remember please how it is correct, I have explained very well. So if anyone have any doubt, so you can ask, otherwise or you can follow NPTEL video what sir has taught already in the week 11. So sir has explained very well, so you can go through also. So this is about your very basic and fundamental of CFD. So now let us move on the second. If anyone have any question you can ask. I'm going to move on the option, the question number 2. Okay, so let me just read the detailed solution. What is written here? The CFD discretize the equation and also domain. Discretize equation and domain. What I have, domain means missing thing. Discretization equation means you are going to convert your partial differential equation in terms of algebraic equation and solve the discretized equation for only the points in the discretized domain using numericals method. So everything is here written very short form. So I have already told you. Now, if anyone have any doubt, let me go the interaction. Okay. NPTEL exam question pattern, MCQ and NPTEL question. Okay. So your NPTEL question is maybe I think 100 marks question, NPTEL question, and you will get some 1 mark question, 2 marks question, maybe sometimes 3 marks question. Actually, I don't have idea because this course is running by, I think, Professor Saud Afzal from IIT Kharagpur. So I am not a TA of this course. I am discussing the previous year questions, so I don't have exact idea. So, but I have idea about the fluid mechanics because my professor in the next semester going to run the fluid mechanics NPTEL. So in the fluid mechanics, actually my professor said the question 1 marks, 2 marks, 3 marks and 4 marks. Overall, I think 80 marks question or 100 mark question. Anyway, the question number will not depend actually in the final your mark sheet, your final marks, the percentage will be calculated. I think 40% marks for your assignment. If you not done your assignment, you please, I think the date of assignment also, the previous assignment date gone. So in the future you for week 11 and week 12 or remaining if week 10, so you do all because 40% percentage of your this assignment. And the rule of NPTEL for question setting, your 25% question will come from your these assignments, the current assignment whatever you are doing in the 2026. So this is about, I know, your the NPTEL final exam. So that's all. Anything, Indrajit, if you want, you can ask. Okay, so if not, so let us move on the question number 2. Okay, thank you. Welcome. So question number 2. The second order, let me just go on the PPT. The second order upwind SOU scheme use. Option A, asymmetric linear profile, symmetric linear profile, asymmetric quadratic profile, and symmetric quadratic profile. So you have 4 options here: asymmetric and symmetric, and linear and quadratic. So you have the linear and quadratic, and symmetric and asymmetric. The second order upwind scheme use. So please just recall your concept and try to write your answer in the chat box. One thing I'll suggest you, if you are going to for final exam, so you have to revise your all assignments from week 1 to week 11. So definitely you will get the more than 50% marks. Okay, so Deep is telling A, asymmetric linear profile, Indrajit telling C, asymmetric quadratic profile. Okay. Other student, all please you can participate also. Your participation matters a lot here because if you are participating here, if you are somewhere wrong, and definitely in the finally I'll show the correct answer, so you will remember for a long time, and maybe this question or any question come in your final exam or any competitive exam or in your university exam. So the participation here is matters a lot, please. Okay, so let me just go for final answer. So second order upwind scheme use your asymmetric linear profile. Asymmetric linear profile, option A is correct. How? Let me just go in detail solution what is written here. The second order upwind scheme, like the central difference scheme, use linear profile. Your central difference scheme use linear profile, but unlike the central difference scheme, your the second order upwind scheme, it is use an asymmetric linear profile. This is why it got the name upwind scheme. So this is all about. So detailed mathematics, what is the second order upwind? Please go detail through your NPTEL videos. So that will help you a lot. So now let us move on the next one. Question number 3. Okay. So here again, very fundamental question. Question number 3. The solution of flow problem is defined at discrete point in the domain is called element, cell, grid, nodes. So please just recall your concept and try to write your answer. Okay, Bala is telling D option, nodes. The solution of flow problem is defined at discrete point in the domain is called elements, cell, grid, nodes. Okay, Indrajit also telling D. Other student please also just participate. So I'm waiting 1 minute. Please within 1 minute you just write your answer in the chat box. Okay, notes. Deep is also telling notes. Okay. Okay, so everyone telling is majority of a student telling the notes. Yes, definitely it will be the notes. As we have seen in the explanation or detailed solution of question number 1 also, here you can see only the point of, here you can see the CFD discretize the equation and solve the domain and also domain and solves the discretized equation for only the points in the discretized domain using the numerical methods, means at points, solve at points, and that point is known as your node. Here you can see option D is correct for question number 3. So remember always, please let me just read the detailed solution. The nodes are the nodes are the intersection of cell in the domain, and these are the point where the flow properties are defined after solving the problem. The flow is not analyzed in continuous point of the domain. Whatever I have earlier in the first question I have told or explained the similar things. So now let us move on the next one. Very fundamental question again. Question number 4. To obtain the derive to obtain the derivative of variable with respect to the coordinates, which of these approximation are used in the finite difference method? Taylor series and polynomial fitting, Fourier series and polynomial fitting, Taylor series and Fourier series, Taylor series and interpolation. Please just try to write your answer for question number 4. To obtain the derivatives of variables with respect to coordinates, which of the approximation are used in finite difference method? Taylor series and polynomial fitting, Fourier series and polynomial fitting, Taylor series and Fourier series, Taylor series and interpolation. Okay, so Deep is telling A, Bala is telling D, Taylor series and interpolation. Deep is telling Taylor series and polynomial fitting. Okay. Other student, please also just try to write your answer in the chat box. This is very fundamental question. Whatever we have solved till now, these all four questions are very fundamental from your safety. So if you are going to for learn the safety, you have very these fundamentals should be very clear to all of you. Okay, so Indrajit also telling A option for question number 4, Taylor series and polynomial fitting. Other student, please also just write your answer in the chat box. I'll wait 1 minute more for other students. So here we are discussing, please. You just write your answer. 1 minute more, then I'll move for the answer. Okay. Okay. So let me just move. Yes, your option A is correct here. Means to obtain the derivative of variable with respect to coordinates, means with respect to x, y, z, you need Taylor series and polynomial fittings. Detailed solution. The, the conversion equation of partial differential from is used by the finite difference method. Sorry, let me just read again. The conversion equation of the partial differential form is used by finite difference method to approximate the derivatives in this equation. Taylor series and polynomial fitting are used. So remember. Again, let me just go for the next question number 5. So here, what is the main disadvantage of explicit scheme in a time dependent problem? What is the main disadvantage of explicit scheme in a time dependent problem? Your the matching solution or your simultaneous equation, small time step size, small grid size. What is the main disadvantage of explicit scheme in a time dependent problem? So please just try to write your answer in the chat box for question number 5. These are the definitely what we have discussed last previous your week 1 to 10. The week 11 and week 12 entirely different because little bit advanced. Your week 10, week 11 and week 12 both are little bit advanced from your basic your fluid mechanics. So please you have to more focus on that if you are going to for higher studies in fluid mechanics. Okay, so Bala is telling C option, a small time step size. Okay, nice. And these are whatever you will learn here. This is not your only limited to your the fluid mechanics things. Whatever you will learn concept here, you will apply for the structural analysis. If you go for the higher studies, like master level studies, so that will help you when you will do the structural part, structural analysis. If you will got the structural analysis stream or geotechnical stream, whatever you will learn. Because nowadays numerical modeling, that is CFD, is specifically for your fluid flow problem. But whatever you will learn here, your the numerical modeling that will be used anywhere in physics also, mathematics also, in your computer science, everywhere you will you need to apply the numerical modeling. So this is the advantage of this course, or specifically week 11. Okay, so Bala is telling 5C. Other student, please also just try to write your answer, or if you not know, you just Google it. That will be help you lot. I'll wait 1 minute more for this question. So please, you just Google and try to write your answer in the chat box. What is the main disadvantage of explicit scheme in time dependent problem? Okay, so let me just show you the answer. Okay, so option C is correct here. That is a small time step size. This is the your problem with the explicit scheme. The main disadvantage, so, for explicit time dependent. Okay, so let me just read the detailed solution. The detailed solution: explicit time based scheme have a limited time step size. Big time step cannot be used. So the total time of computation required to solve the scheme is very large when compared to the implicit schemes. Remember. So these are the fundamentals. Now let us move on to question number 6. What is the last order of accuracy for the second derivatives? First order. Oh, sorry. What is the least order of accuracy? Sorry. What is the least order of accuracy for second derivatives? First order, third order, fourth order, second order. What is the least order of accuracy for the second derivatives? Again, from very fundamental. Least means here the minimum. So please just try to recall your concept. Okay. Indrajit is telling second order. Nice. Other student, please also try to write your answer. Okay. Pala is telling D, second order. Both you are telling the second order. Other student, please also just try to write your answer. Deep is telling second order. Okay. So all you are telling the second order. Most of the student telling the second order. So yes, definitely the second order. Let me just read the detailed solution. The least possible order of accuracy for second derivative is 2. There cannot be a first order second derivative, as the second derivative need term less than the second order for the approximation. So there cannot be a first order second derivative, as the second derivative need term less than the second order for the approximation. So remember please. So for least order of accuracy for second derivative, it is your second order. Next question. Question number 7. Very fundamental, very basic. From your also you can give this answer from your basic fluid mechanics. For a no slip condition, which of these about velocity component is true near the wall boundary? Option A, u is equal to 1, v is 0, w is 0. B, all three component of the velocity is 0, u, v, w. Option C, u0, v1, w0. Option D, u0, v0, w1. So you have here the four option. So whether u will 1, v will 0 or w will 0. So you just think, recall your concept. Okay, so Bala is telling B option, that is all three component of velocity is 0 near the wall boundary, which is known as your no slip condition. You are telling, the Bala is telling. Okay, other student, please, what is your perspective of this question? So please just try to write your answer in the chat box. All velocity component is 0. Deep is telling. Okay, nice. You are also telling the B option. Other student, please. I'll wait 1 minute more. This is very fundamental question, and from you can write the answer for this question from your very first or very beginning of the classes of fluid mechanics or hydraulic engineering. Okay, Indrajit also telling B option. Okay, most of the student telling the B. So let me just go ahead. So yes, definitely your B option will be correct. How? The no slip condition. No slip condition means your velocity is 0. Velocity is 0 means velocity is what? Velocity is your u I plus Vj plus Wk. This is your velocity. Means all three direction. So if I show you the three-dimensional things like the channel uh, like this. Okay, so three dimension is very difficult to draw here in a very short period of time. So means your, let me just show the two-way 2D or 3D also I can show you, no issue. This is your, let us suppose the plate, and this much here depth is flowing. So this is your y direction, this is your x direction, and this depth is z direction. So means no slip condition means at the wall boundary. This is your wall. So at the wall, this your V will be 0, X will be 0, and Z component also will be 0 here. Z component means W, or here is U and V here. So this is the very basic diagram for your no slip condition in all three dimension. Okay, so now let us move on the next question. This is very fundamental. So let me just read the detailed solution. No slip is ideal condition with the highest viscosity. Here the fluid is relatively stationary with the wall, and all of velocity component are 0. Therefore UVW will be 0. Let us move on the next question. Question number 8. Okay. So defining the flow geometry and the domain discretization fall under pre-processing stage, post-processing stage, simulation stage, all of this. So now you are moving ahead from your fundamental to application, towards the application. So this question is about how you will utilize your CFT things. So just think and try to write your answer in the chat box. Okay. So Bala is telling A, pre-processing. Nice. Other student, please also try to write your answer. Defining the flow geometry and domain discretization fall under pre-processing, post-processing, simulation, all of this. So please just try to recall your concept and try to write in the chat box. So I'll explain here also about the pre-processing. post processing and simulation. What is the actual meaning in terms of CFD? So I'm waiting for your answer. I'll wait 1 minute or 2 minute more. So may other student can think and write your answer in the chat box or recall your okay. So Indrajit also telling pre, that is A option. Other please. These are the very today whatever we are solving. These are the very fundamental question of CFD. CFD have lot things than what we are discussing here today. So this is not as simple as like the whatever you have learned fluid mechanics last 10 week. So but this is not very difficult. Anyone cannot learn. Definitely if you will give time, you will learn. And once you will learn, so you will get lot of confidence about CFD and knowledge also about the fluid and what is the now what is going on in the fluid mechanics, how you will solve the big problem with the simple your with your laptop. So also these are the possible nowadays. Lot of free software, free tools are there for CFD. Also commercial software are there, like commercial software are ANSYS, Flow 3D, and free softwares or free actually softwares you can say, but not exactly software. The open form, Riff 3D, these are the open source software. So please, okay, so let me just go ahead with the solution. So here definitely it is pre-processing. So me, what we will do, once you will ready with your the equations, once you will ready with your equations and code, definitely you cannot solve the equation by your hand. So you need some code. If you are ready with this, so now you have to define your problem. So let us suppose I am going to solve what will happen if water will flow over the hump. What will happen? How the flow behavior? Or what will happen if I'll put, oh, this is your uniform. If I put a shell, that is breeze spear, or you can say the cylinder in the flow path in open channel, what will happen? So these are the problems. So once you will set the problem, now you have to, this is your geometry, defined geometry. We have defined the geometry. So sometimes for defining geometry, you need some CAD model. Like I'm using the your AutoCAD, also SolidWorks. So these are for defining your geometry. Discretization, there are tools are there, so you have to discretize. Discretization, lot of methods are there, whether you are going to choose square meshing, whether you are going to choose triangular meshing, tetrahedral meshing, or others. When you will go deeper and deeper in CFD, you will learn the many things. So this is first to be predefined. That is pre-processing. Means you have to very clear with all these things. Now, post-processing is what? So after that comes simulation. Simulation means you will apply these are the equation in your domain whatever you are, or the nodes or points. You will apply the all equation and you will try to see what is happening. You will solve, actually not see what is happening, you will just see. Then after the simulation complete, you will see the result part. This is your means, this is your first the preparation, then this is your the means whatever, let me just correlate with your exam. So first you will prepare the exam, then you will give the exam or write the exam, then after you will see the result. So similar things here, first you will preparation, then the examination, then result part. So these are the three things. So in the result you will see what kind of parameters. Velocity you can see in all three direction, u, v, w. You can also see the turbulence kinetic energy. You can also see the shear stress. You can also see the dissipation. So a lot of things are there. You can also see the vorticity. Whatever you have learned in the last weeks, vorticity also you have learned. So anyway, velocity also you have learned, shear velocity also you have learned. Everything you can see. That is definitely very fascinating kind of thing, the CFD. So okay, so that's all about this question and little bit explanation about the pre-processing, post-processing and the simulation. So now let us move on the next one, or let me just read what is written here. Detailed solution. Pre-processing stage involved defining the problem geometry, discretizing flow domain, that is meshing. This is also known as meshing. Also I have already told you in the very beginning, that is the first question was about these things only. Now we'll move on the next one. Okay, if anyone have any doubt, let me just go on the Google Meet. If anyone have any doubt, you can just write. I'll give you very quick answer. Otherwise, I'll move on the next one. Question number 9. Anything? Okay, you just write your, if you have any question, you just write in the chat box, or let me just go on the PPT for next question. Question number 9. Again, from your the fundamental, a central finite difference approximation of the derivatives d square by dx square can be written as option A, phi I plus 1 plus 2i plus phi I minus 1 del x square. B option, phi I plus 1 similar minus 2i. Here is plus 2 phi I, here minus. Similar thing. Option C, phi I plus 1 plus 2 phi I plus phi I minus 1 by 2 delta x square. The similar here minus only. The similar as option C and only minus here. So you have 4 options. Now you just think very not very fundamental or not very basic. If you have idea about the Taylor series expansion, then you can give the answer for this question. Otherwise, you just recall first. If you not know, you just Google. Okay, so Bala is telling B option. Nice. Other student, please you can just Google it and how it will come. How the Taylor series expansion, how we will do the Taylor series expansion, and after expansion of Taylor series, how we will get the answer. Please just try to write your answer in the chat box. Anyway, Bala is telling B option. Nice. Other student, please also just try to write your answer. So I'll wait 2 minutes. After that, I'll show you the answer. or anyway, I'll just here give the brief how you will expand the Taylor series. I think solutions are there, so I'll show you the solution. Okay, so just please try to write your answer. I'm waiting for your answer. So please just try to write your answer. Okay, so Indrajit also telling B option. Nice. Okay, so now I'll go for the final answer. So here your B option is correct. How? Your you will write the approximation. This is not exactly. Remember please. Here the approximation term is used. You are not going to write exactly. So remember. Tau square phi by dx square. This is not exactly your phi I plus 1 minus 2 phi I plus phi I plus 1 divided by del x square. This is not exactly. The other terms are there here. This is not exactly. This is approximation. Remember. Now, how this equation come? So Taylor series expansion. So using the Taylor series expansion, you will get how? How you will get? So you have delta, or you can write like that: phi is equal to x plus delta x, or phi I plus 1. So this is delta x is increment. Delta x is increment. Remember please. So first your phi I plus delta x del phi by del x I plus delta x square 2 factorial your del x square phi by del square phi by del x square I plus these are the things. Similarly, your phi x minus delta x or phi I minus 1. So you will write, here it is written, here you can see your phi I minus delta x del phi by del x plus delta x square 2 factorial del square by 2 phi, and here minus. Now you have two equations, one for delta x plus 1, delta x minus 1, here you can see. Now when you will add this, after adding the things will be cancelled. Here you can see the all the term is there, but it is not written here. The higher order terms is not written here. The one question we were discussing, the least order for second order. So least order is you have to maintain this least order. There is second order you have to maintain. Okay. So after that the third order will come, fourth order will come. So the higher order will can eliminate for approximation kind of things. Now when you will add, you will get the final answer. Means when you will add, so what you will get? You will get del square phi by del x square from here, and phi 1 plus I 2 phi I and plus phi I minus 1 delta x square. So very simple. This is the discretization method, but you have to remember the expansion. How you will expand your equation. How you will expand the term, that is this one, phi delta x minus 1 or delta x plus delta x. So these are the very common things in CFD. You have another method also. This is your one, you have the forward difference method, another you have the backward difference method, another this is your central difference method, another you have the lot of methods are there. So this is the different method. Another you have the finite element method, finite volume method. Generally in the fluid mechanics, for the very we use finite volume method, remember. But for simple model you can use also the decision, but accuracy will not as much as your finite volume method, remember. Okay, so here is finite element method. Fundamental things. While using a finite element method, one has to approximate what? Boundary conditions, integrals at grid face, derivatives at grid points. Option D, shape function and weighing or the weighting function. Shape function or the weighting function. So you have four options. While using a finite element method, one has to approximate boundary condition, integrals at grid face, derivatives at grid points, shape functions and weighting function. So I'll wait 2 minutes or 3 minutes. I can wait. You just recall your concept. Okay, Bala is telling D option, the shape function and the weighting function. Nice. Other student, please just try to write your answer in the chat box. So just I'm taking.
Plasticky.
Yes, sir.
Good, good. Very good.
Okay, so Deep is telling D option, shape function and the weighting function. So other student, please also you can write your answer in the chat box. So 1 hour remaining, sir. So 5 to 7.
5 to 7.
Yes, sir.
Finite difference you were teaching.
No, sir, not teaching. Actually, the Professor Saud Afzal had teach the CFD things in the week 11.
Okay.
So just I am solving the previous year questions, assignment questions.
CFE.
CFD, yes, sir. So, okay, so Deep is also telling D. Other student, please also just write your answer in the chat box. Okay, so if not, so I'll just go for the final answer. So yes, D option is correct here. While using the finite element method, you have to approximate what? Your shape function as well as the weighting function. So remember please. So the detailed solution is there. While using a finite element method for solving a problems, shape function and weighting function are approximated. Integrals at grid face are approximated for finite volume method. Remember please what I was discussing. You have finite element method, finite volume method. Here for finite element method, your save function and waiting function are approximated. This is very fundamental. So remember please, if you will go for any job on the base of, if you will tell the the fluid mechanics and CFD kind of things, maybe one can ask you, this is very fundamental, the finite element method. So what you need to approximate the save function as well as waiting function for and the for finite volume method, integrals at grid phase you need to approximate for finite volume method. Derivatives at grid points are approximated for finite difference method. All three here it is written. For finite difference method, you will go with you need to approximate derivatives at grid points. For finite volume method, integrals at grid phase. For finite element method, save function and waiting function need to approximate. So these are the very fundamental. All question was from very fundamentals of CFD. So now we can move for the next question. The question from your, if anyone have any question you can ask, otherwise we'll move on the next one. Okay, so let me just move for the next questions. So we have also solved 2025. Now I'm going to move for 2024. 2024 assignment of hydraulic engineering. Okay, so now I'll take just 5 minute break. If anyone want to take, you can also take. So I'll come back again after 5 minutes. So now we can start the your 2024 hydraulic engineering questions. So the question one is about, let me just go on PPT. Yes, the question one is about the CFD carried out observational, let me just take the pen, observational experiments, analytical experiments, field experiment, or numerical experiment. CFD carried out observational experiment, analytical experiment, field experiment, or numerical experiment. So please just try to write your answer in the chat box. Okay, so Deep is telling for one, you are telling D option. Bala is also telling for one is D option. Okay. So other student, please also you can just write your answer. Okay. So yes, definitely. As we have discussed a lot, we will solve the CFD. Actually, we do the numerical analysis. We solve the your first continuity equation you have in your hand, your Navier-Stokes equation. Then Navier-Stokes equation convert in Reynolds average Navier-Stokes equation. Then you need to apply the discretization of your these equations. Then you need turbulence models and apply these all the things you will convert in the your this the simple equations like the your using the finite element method, finite difference method, or finite volume method. Then you need to write a code combined all this equation how it will move. Then you will solve numerically. Numerically means using the numerical model, using the some code. Also, you can solve this equation by your copy and pen, but not possible for a complex problems. You can solve only one step and call and one step. Yes, if you go for the next step, that will be very difficult. Just for understanding, you can go for pen and copy. Otherwise, you have to write the code with combining all these equations. Okay, so definitely we solve in numerical. We do the numerical experimentation kind of things. Now we'll move on the next one. So here you just see the CFD use numerical experimentation to obtain the flow properties at discrete points. Computer program are used to carry out these experiments. Remember. So we'll go for the next question. Next question is the reason of interest for analysis in safety is known as the reason of interest. Here we are talking about the reason of interest. So don't be confused. The cell, domain, mass, grid. Very fundamental question from your pre-processing. These question from your pre-processing. What we have learned in the previous one, the pre-processing, post or simulation, then post. So this question from your pre-processing. So please write your answer in the chat box for question number 2. The reason of interest. Okay, so Bala is telling for 2B domain. Other student, please. Okay, Indrjit is also telling for question number 2B. Okay, nice. So other student, please also you can write your answer for question number 2, whether it will be cell, domain, measure, grid, or you can write the option also A, B, C, D. I'll wait 1 minute. Just recall the previous whatever we have solved, the 10 question from 2025. I have explained many things. So that will help you in this assignment 2024. So just recall what I have explained. I have been, I think, explained already about this. Again, I'll explain here. Okay, so let me just explain and try to recall. So actually, for solving, let us suppose you have the your for pipe problem, you have the pipe of length this much, like that. You have pipe of length like this. This is your pipe. Water is flowing, going this direction, going this direction, downward. So now you reason of interest means you need to see if you can understand one thing here. If you will just break these things, what you will see up to here, your domain is what? Symmetry kind of things. Means whatever the result you will get this side, the similar result you will get this side. When you will go for solving, what will happen? When you will go for solution, the things you need to consider one thing. So the time taking, when you will run the program, the computer program, it will take time. But let us suppose the similar result, as you know, the symmetry is there, similar result will come. So you can run only the half part. So this part is known as region of interest. If you are running for full part, this is also known as your region of interest. Region of interest. This is all. So you need to discretize all this your region of interest. And in terms of CFD, the region of interest is known as domain. Remember, please. This is your domain. Very fundamental. So here you can see the detailed solution. The region of interest for solving a particular fluid flow problem is called domain. The first step in pre-processing is to define the geometry of this domain. First, yes, definitely. The first step, define the geometry. Then meshing. Then you apply the initial condition, boundary conditions. How the flow is goes, let me just explain you. First you will draw the geometry. Then for you need to meshing the things, you need to mesh. You need to apply the mesh of your domain. Then you need to apply the initial condition, boundary condition. What is the boundary? Whether it is the no slip condition, whether here is the velocity is how much, here is the what is the condition of outlet. These are things. What is the condition of z minimum, z max? So you have the 6 boundaries. What? For 3D problems, x min, x max, y min, y max, z min, z max. So you have the, here you need to define your boundary conditions. Then we need to apply the initial conditions. What is the initial? Whatever you will apply the initial condition, in each your grid, the initial condition will be maintained. If you are applying, let us suppose initial condition you are applying, my fluid domain have velocity 0.1 meter per second. So it means at each grid or each point you are applying 1 meter per second. So remember. So very careful before applying the initial condition or boundary condition. You have to have very confident about your flow domain or flow problems. This is matters lot. Also the your domain, that is mesh size, is matters lot. Also the turbulence your the selection of turbulence modeling also matters a lot. What is turbulence modeling? That is how many turbulence modeling. So this is your K epsilon modeling, K epsilon turbulence model, K omega turbulence model, renormalized, renormalize RNG, renormalize group K epsilon. This is K epsilon. K here is turbulent kinetic energy. E here is your dissipation, which is related to. Also, you have the large eddy simulation. So these are the turbulence models. So result will vary with all these things. So you have to very clear with which turbulence model work best for your problems. So you have to background of this. So these are the some basic. So let us move on the next question. Next question is okay. So CFD package what here is telling, CFD package is nothing but it is the already program is there. Means already the Rance equation and the discretization, everything is already written in the programming form. That is the CFD package. It may be the open form, it may be the RIF 3D, it may be the your ANSYS, it may be the your flow 3D already. So CFD package solve the algebraic equations. I think you are able to connect what is algebraic equation means. You need to convert your RANS, that is partial differential equation, you need to convert in terms of algebraic equation using what? Using your finite difference, finite element, finite volume. So you need to, I think you are able to now connect very well. So CFD package solve the algebraic equation of flow using direct method, iterative method, analytical method, trial and error method. So now little bit advanced, the question is going little bit advanced. So hope you will understand. So for question number 3, the Bala is telling D, trial and error. Nice. Other student, please also try to write your answer. So these are some basic kind of things about CFD. Once question will come, I'll give you whatever I have. I'll give you all. So please just try to think. If you not know, I have already told you, you just Google. First you try to recall your concept. If you're not able to recall, you just Google it and try to write your answer in the chat box. By doing this, you will remember for a long time. Okay, so Deep is telling B and Indrajit is telling B, that is iterative method, and Bala is telling D, trial and error method. Okay, no issue. So a bit contradictory here. So let me just go for the final answer. So your final answer is iterative. Remember please, option B will be correct. In CFD package, the algebraic equation will solve iteratively. What is written in the detail? The physical phenomena make the algebraic equation complex and nonlinear. Hence, an iterative method is used in CFD package to solve these equations, like your Newton-Raphson method. As you know, for Newton-Raphson method, your iterative kind of things. So such type of methods. Means what I am telling the Newton-Raphson here, just you need to uh, make it understand you what is iterative kind of things. Okay, so now let us move on the question number 4. Which of these will fall into the post processing categories? So hope you will give the answer correctly, because I have already told you the pre-processing, simulation, post processing. So I'm seeking answer to all of you. Very correct. Option A, definition of defining of boundary conditions. So here defining should be term there. And the grid generation, flow visualization, and discretization. So what option will correct? Which option will correct? Please just try to write your answer. So Bala is telling C, flow visualization. Okay. Other student, please. So again here I'll explain. Maybe some student which here not present will see later, or maybe, so for that some student what can do, just try to see from the not beginning, just from the middle. So if let us assume some student try to see from the question number 4, if I'll not explain here, that will be difficult for that question or that student. So I'll explain, but very briefly, not like previously. So Indrajit is also telling C, Deep is also telling C. That is flow visualization, definitely. Okay, so you are asking the discretization. Yes, definitely. This discretization is the pre. Yes, definitely. You have the pre-processing and you have the post-processing and you have the simulation in between. So in pre-processing, you need to define your geometry, define your domain, discretize, apply boundary condition, initial condition, everything. Then you run the simulation, run the code. Then after running the code, you will get some datas and you just try to visualize. This is known as your post-processing. Visualize means you will try to see the velocity in all three dimensions direction, and the shear stress and vorticities and other fluid parameter, pressure also sometimes. Now let us move on the next one. Okay, so let me just read detailed solution. Post processing is the final step in the CFD after pre-processing and solving. Solving means your simulation, and this uh, involves various method of visualizing the flow as well as getting quantitative information. Various method of visualization. So like if you are try to see the velocity, you can see in the color format. Let us suppose if this is your open channel, that is 3D open channel, like that. The water is entering from here and going out here, and here some object you have put it, like cylinder you have put it here. Here you have the cylinders, that is spur. So if you want to see what is happening near about this, that is just upstream of your breeze spear, just downstream of breeze spear, so you can see the cross section also. So like that, cross section, that is your breeze spear here, and at the level of breeze spear, at the middle, at the middle of breeze spear. So you are looking this one, the middle one. So you can see this by the color also, the colorimetry. That is, you will get some here the color bar, minimum to maximum. So here the color will you will visualize. You can visualize through the your stream lines. You can visualize through the vector also. So this is the meaning. Okay, so now we'll move on the quantitative information. You will get some idea about it. Here, let us suppose the velocity here will be the near the this spur. Your velocity, maybe the streamwise velocity will be the less, but the secondary current and all will be the more. So this kind of, but more means how much more, whether it is uh, 1 meter per second or 0.5 meter per second. So quantitative information you will also get. So now let us move on the question number 5. Very important. Okay. So which is the input part of the CFD problem? Post processing, flow visualization, pre processing, or solving? Input part of the CFD problem. So please just think and recall. Just try to understand. Already I have told you. So just try to understand. Very important. Which is the input part of a CFD problem? Okay, so Bala is telling for question number 5, C option, pre-processing. Nice. Other student, please also try to write your answer. First, try to recall. If you not know, you just Google and try to write here. While doing these kind of things, you will remember for a long time, as I have told many times. If you not know, then you do just Google kind of things. If you know, if you have remember, just recall what, just read question and read the option, recall, try to recall. Okay. So you are telling the pre, Indrajit also telling pre, because first step, that is okay, 5C. Got it. So today what we are solving the CFD problem, that is very different what we have solved already the 10 assignments. Also maybe I think week 12 also very different from your previous one. So this is the specialty of this course, hydraulic engineering. These 2 weeks, week 11 and week 12. These 2 weeks make the special hydraulic engineering course. Okay, Deep is also telling pre. So if you are telling, so definitely it will be the pre, as I have discussed also. Input means what? Input means the boundary condition, initial condition, you need to input. Input means mesh size, size of the mesh, time step also. So these are the inputs. And what you are going to select the turbulence parameter, whether you are going to select the K epsilon, K omega, RNG K epsilon, or you are going to apply the large eddy simulation, or other also the other turbulence model also there. So what you are going to apply, what is the physics, whether you are going to apply the water, your fluid density, whether you are going to take the water 1000 meter cube per second, sorry, 1000 kg per meter cube, whether you are going to some oil, that's depend, whether you are going to run the air. So for air also you need to select the density, what will be the temperature also. So many things in CFD you need to put, you need to give as an input, then you will give the your answer near to nature, not exactly the nature, but near to nature, you can correlate the things. Hope you understand. So now let us move, let me just read the detailed solution. So here option C is correct. The pre-processing part of CFD problem is the first step before starting to process the problem. This is where the input are specified, and what are the inputs already I have told you. So the next question. Okay, so next question is, which of these models would be best for flow over submarine? So we are going to model submarine. You are going to see the flow over submarine. So you will apply the 3D Navier-Stokes equation for compressible flow without a turbulence model. 3D Navier-Stokes equation will be common, but in the option B for 3D Navier-Stokes equation for incompressible flow without turbulence model, 3D numerical Navier-Stokes equation for compressible flow with turbulence model, 3D Navier-Stokes equation for incompressible flow with turbulence model. So here the question is roaming around compressible, incompressible, turbulence model. Okay, turbulence model and compressible, incompressible. Anyway, the 3D Navier-Stokes equation is there, means the in all options. So you have to think about whether you will go with the without turbulence model or with turbulence model, compressible or incompressible. So you have to think very clear. Okay. So based on your understanding, so Deep is telling D option, Navier-Stokes equation for incompressible flow with turbulence model. Bala is also same telling option D, 3D Navier-Stokes equation for incompressible flow with turbulence model. Nice. Other student, please also try to write your answer. Just think, because here you need to apply your fundamental, the fluid mechanics what you have learned from week 1 to week 10. That knowledge will help you to answer this question, please. Very fundamental. First you try to think whether submarine, what is submarine and where it need to put, where it need to flow. What is submarine? If you know the submarine, then you just guess whether your submarine will flow, navigate in your compressible fluid or incompressible fluid, whether near the submarine the turbulence kind of things happens or not. So if you are able to correlate of these things, definitely you all people give the answer in very correct way. This is a way of thinking. So just try to think, please. Anyway, two student tellings, uh, D and okay, both are telling D. So I'll give 1 minute more for other students. Then I'll go with the solution. And one thing I'll tell you, please, I think in the next week, next Sunday, I'll take the class, and another, the summary class also I'll take. In summary class, I'll solve from week 1 to week 12 the question sets. The lot of questions, maybe the 100 question I'll solve that day, so you can attend. That will be very helpful for your revising the all assignments as well as for final exam. So after Sunday, maybe on Monday I'll take. Anyway, the NPTEL team will inform you through mail, no issue. Okay, Indrajit is also telling D option. Okay, nice. Everyone telling D, so hopefully D will be correct. Yes, definitely. Why? Because in submarine flow in water, water you know already, the incompressible fluid, and around the submarine turbulence are there, so you need to apply the turbulence. Then you will get the things. What is happening? So definitely you will go with the option D. 3D Navier-Stokes equation for incompressible flow with turbulence model. What is written in the detailed solution? Let me just read for you. Incompressible flow is cohesion as well. Cohesion as the flow of water will mostly be incompressible. A similar thing. The turbulence model is cohesion as the flow properties will get abrupt change due to high Reynolds number. Oh, sorry. Here is the incompressible flow is chosen as the flow of water will mostly be incompressible. Turbulence model is chosen as the flow properties will get abrupt change due to high Reynolds number. Okay, so let me just move for the next question. Question number 7. Okay. So what would be the major difference between aerodynamic and hydrodynamic analysis? So here also very important things. Now this question from your applications. So in aerodynamic and hydrodynamic, the difference for temperature, Reynolds number, velocity, domain. Again, this question from your just you can think and you can just write answer. Just memory based question. Yeah, but you have some background of fluid mechanics. Okay. So question number 7, please. Seven B means Reynolds number. Okay, nice. So here you need to just write the difference. Just think the difference of aerodynamic and hydrodynamic analysis. Analysis means you are going to solve the problem of aerodynamic, that is the flow around your aeroplane. Hydrodynamic means flow in pipe, flow in channel, that kind of thing. So Bala is also telling, okay, Bala is telling C and Indrajit telling B. Other student, please. Other student, please just write your answer in the chat box. Okay, so domain. Deep is telling domain means option D. Okay, here all questions are very contradict, not matching. So let me just show you. Here is the Reynolds number. Why in aerodynamics? Let me just read the detailed solution, then I'll discuss. The Reynolds number of flow would be the major change as the density of viscosity as the density and viscosity of water will be higher than the air. Aerodynamic means air, as I have given the hint you during the what the question. Aerodynamic means air, and hydrodynamic means the flow in pipe and what channel. So definitely air. So definitely density and viscosity will be very very different, very very that is less you can say compared to water for air. So Reynolds number definitely will change, lot change. Therefore, while modeling a hydrodynamic flow, the care should be taken about Reynolds number. Remember. Now, from you can say this question from your mathematics. Also, you can say CFD. CFD is mathematics. Nothing. You can say the mathematics of fluid. CFD is you can say your mathematics of fluid. Okay, so which of these is not a type of flow based on their mathematical behavior? Which of these is not a type of flow based on their mathematical behavior? Circular, elliptic, parabolic, hyperbolic. Okay, so please just try to write your answer in the chat box. Just think about it. Which of these is not a type of flows based on their mathematical behavior, whether circular, elliptical, parabolic, hyperbolic? Means here meaning is this question meaning whatever you have the partial differential equation, if your partial differential equation will become circular, hope you know how we will calculate the circular, whether your elliptical type or parabolic and the hyperbolic. So whether your equation is circular, elliptical, parabolic, hyperbolic, so the correlate from that things, the your equation mathematics and then the options. Okay, so you are telling the circular. Deep is telling circular. Bala is also telling circular. So if not anyone know, you just Google it. So that is from question you can say from mathematics also. You have some mathematical background for whether your the partial differential equation, that is Navier-Stokes equation and other equations will follow the circular, elliptic type of solutions, parabolic and hyperbolic. Okay, so both you are telling the circular. So okay, let me just show you the answer. Definitely it will be the circular. The three type of flows based on the mathematical behavior of elliptic, parabolic and hyperbolic. These behaviors decide the method used to solve the mathematical model of the flows. Remember please. So before you are going to solve any problem, you first try to find out whether your equation elliptic type, parabolic and hyperbolic. Based on this, you need to select your mathematical model. Why? Because once you will, let us suppose if you not know, if you will not check these things, so you will try to with elliptical, maybe you can try with the parabolic, maybe you can try with the hyperbolic. You will fail here, you will fail here, maybe you will success here. So this time will be lost. You can lose these times. Let us suppose your problem is parabolic type of and you are not checking these things. Let us suppose if you are solving, if you start with the parabolic, then it is okay, you are solving the very much very good. But by default, by mistake, you are going to solve with elliptical then parabolic, so this time will be lost. So you have to check very carefully. Once this is very simple check, I think 4b minus 4ac. And what is b minus 4ac? Like greater than equal to 0? That's that kind of things. I am not able to recall very clearly. So these kind of things you have to check. Just you can Google, you will find out how you will check the whether your partial differential equation elliptical, parabolic, hyperbolic, circular. So definitely the formulas are there. Okay, so Laplace equation is elliptic in nature. So what is Laplace equation? So del square phi by del x square. Here you can put the other parameters also. Del square phi by del y square plus del square phi by del z square is equal to 0. Here you can put the velocity UVW. Okay, so now we'll move on the next one. Question number 10. The classification of partial differential equations are governed by their highest order derivative. The partial differential equation, the classification of partial differential equation are governed by their highest order of derivative, their least order of derivative, the number of term, the constant. So here the answer is for question number 10, their highest order of derivative. Their highest order of derivative means del square by del x, del u by del x whole cube. So here we'll follow the order. Remember please, not the degree. So if this is equation, so order of this equation is 2 and degree of this equation is 1. Will not switch here. Whatever you are looking the term for order, the same term you need to look for the degree. If here suppose that 4, then your order is 4 and degree is 3. Okay, so now let us move on the next question. Question number 11. The stability is a property of a partial differential equation, discretized equation, discretization process, and mathematical modeling. The stability is the property of which? Just try to write your answer, please. For 11, the Indrajit is telling D option. Okay, that is mathematical model. The stability is a property of a mathematical model. Nice. Other student, please. C. Bala is telling C, discretization process. The stability is a property of a discretization process. Nice. Other student, please. Just try to recall what sir has taught in the previous week, week 11. Okay, so let me just go for answer. Yes, definitely it will be the B, discretized equation. Your stability is a process of a discretized equation, is a property of a discretized equation. So stability is not a property of a discretization process. It is a property of a resulting system of discretized equation. This can be analyzed mathematically for the system Stability does not exist for a partial differential equation or mathematical models. Remember, these are fundamental. Okay, so now the next is your small eddy scale are known as small eddy scales are known as your Bachelor scale, Taylor macro scale, Kolmogorov macro scale, integral length scale. So your small eddy scale is Kolmogorov microscales. Remember. Okay, so here the detailed solution. The smallest eddies with dominating viscosity are called the smallest eddies with dominating viscosity are called Kolmogorov microscales. Kolmogorov microscales means what? The small eddies. The small eddies with dominating viscosity means the eddies with viscosity is dominating near the eddies whatever you have, the very small, and that thing is given by the Kolmogorov scientists and to Kolmogorov who carried out work on the structure of turbulence in 1940s, the Russian scientists. So then on the respect of this study and Kolmogorov, such eddies known as the Kolmogorov microscale. So that's all about your 2024. Now let us move for 2023, assignment number 2023. So this is your 2023, same hydraulic engineering. So we have already solved 2025 and 2024. So first question, Navier-Stokes equation are the system of equation where it is coupled, uncoupled, exponential, radical. So this question we have solved in I think week number 10 or week number 9, I don't remember, but we have solved previously. So let me just see whether you have remembered or not. Okay, so you are telling 1, yes, definitely 1 will be correct. So you have remember. So Navier-Stokes equation are called coupled system of equation because all of the equations should be solved to get dependent variable. Equation cannot be solved separately to get the unknowns. Means you are if you are solving the number set of equations simultaneously, then for calculating the means if you are solving the equations to get the dependent variables, Navier-Stokes equation are solved coupled system are called coupled system of equation because all the equations should solve means for getting the variables. Let us suppose you have the Navier-Stokes equation, you have variable u, that is x, y, z, and your pressure. So means x, y, z the velocities. So for getting this u, v, u, v and w. For getting this, you need to solve all equations. Then you will get. Next. Okay. So answer is visible, no issue. The diffusion term are not included in the continuity equation, y momentum equation, z momentum equation, energy equation. So it is z momentum equation. Diffusion term are not included in z momentum equation of Navier-Stokes equation. Means you have Navier-Stokes equation all three direction x, y, z, but in the z the diffusion term is not included. So what is Navier-Stokes equation? So already I have taught very well in I think in previous week, I think week number 10. Okay, so detailed solution, mass diffusion of continuity equation are in general not included in the Navier-Stokes equation. This is because most of the fluid flow and thermodynamic process do not include any change in concentration, which is mass diffusion. Next question, question number 3. Okay, so turbulence problem particularly depend on this term of Navier-Stokes equation. So which term? The turbulence problem particularly depend on whether rate of change of term and the convection, diffusion or the source. Turbulence problem particularly depend on what? Okay, so you are telling the convection. Okay, so your turbulence problem depend on the diffusion term in particularly depend on diffusion term of Navier-Stokes equation. Remember. Next question, what is detail? The turbulence is caused by abrupt change in velocities, particularly to the flow, and this is term can be given in viscosity term. Diffusion term of Navier-Stokes equation holds the viscosity term. So without diffusion term, we cannot model turbulence. So you have to have diffusion term. So which is your epsilon, which is your omega, which is related to these terms. Okay. So question number 4. What are the major type of boundary condition? Wall symmetry, inlet outlet, or your the dilate and Newman and initial and physical. So definitely option C will be correct here. Dilate and Newman. Next, which of these does not come under partial differential equation? Laplace, equation of motion, 1D wave equation, heat equation. Under partial difference, which one is not the partial differential equation, you can say? So Deep is telling C. You are telling C means 1D wave equation. Let me just check whether it will be correct or not. No, the equation of motion. The equation of motion not come under the partial differential equation. The equation of motion come under ordinary differential equation. Laplace equation, wave equation, heat equations are all partial differential equations. Next question. So whatever we I was discussing the same thing here. If we are solving K epsilon model, the value of K and epsilons are either specified or estimate at the inlet, are specified or estimate at outlet, need not be specified or estimate anywhere, are not estimated. So just please, I think I have discussed about this. During the discussion, you are telling A option. Definitely, we need to define or estimate at the inlet. I have already discussed about this. So most of the accurate, I think we have solved the similar problems in the different way. The most accurate solution can be achieved only if K and epsilon are specified at the inlet boundary, where if it is not possible to provide, CFD code can estimate these values using formulas. Next is discretization of the physical domain of interest result in boundaries, discretized equation, discrete cell or exponential equation. So this is a basic question, memory based question. So discretization of physical domain of interest result in A option. You are telling the boundaries. The engineer is telling the A option and the discretized equation, discrete cell or exponential equation. Okay, so discretize of physical domain, let me just explain you. See, definitely C will be correct. What is discretization? Let us suppose you have some flow domain like that, the pipe flow or open channel flow you have. So discretize means you are need to calculate the velocity within this pipe. So you need to discretize this. You need to discretize means you need to divide these things, your flow domain, in the part by part. So what you are getting? You are getting discrete cell, first cell, second cell, third cell, fourth cell, like that. Next one, the equation of discretization is the process of converting open from closed form linear or quasi-linear partial differential equation into discretized equation. So it is B, that is closed form equation. Discretization is the process of converting closed form partial differential equations into discretized equation. The closed form continuous partial differential equation are converted into discretized equation suitable for numerical simulation. Analytical solution of these closed form partial differential equation will give continuous equation which can be used to get flow variable at any desired point in the domain. Next question. Eddies in turbulent flow result in high diffusion coefficient, less diffusion coefficient, high value of the source term, low value of the source term. Eddies in turbulent flow result in. So please, if you are able to write your answer, you can write for question number 9. Quick please, we don't have time. You are telling A option. Okay. So high diffusion coefficient. Yes, definitely it is correct because the eddying motion of the turbulent flow, heat, mass and the momentum are effectively exchanged, so the value of diffusion coefficient of heat, mass and momentum are high. So close Rans equation, Reynolds average neighborhood equation, we need incompressible flow model, DNS model and turbulence model and the SGN model. So option C, we need turbulence model. I have discussed about this lot. So it is impossible to derive a closed set of Rans equations. So some approximation in the flow model are done. These approximations are called turbulence model, and this usually means prescribing the Reynolds stresses and turbulent scalar flux in terms of the mean flow quantities. Next question. The difference between the exact analytical solution of partial differential equation and its numerical solution is R, round off error, discretization error, iteration error, modeling error. So it will be discretization error. The difference between exact analytical solution of partial differential equation and its numerical solution, its error, which will be discretization. So we have to very careful about the mesh sensitivity analysis if you are going to solve a particular problem. Mesh sensitivity analysis, you will take first 1 centimeter the cell size, then you will reduce 0.9 m, the 9 mm, then 8 mm. So like that, on which mesh size you are getting exact result, the correct result. The correct result means whatever you are expecting the behavior, whether you are getting or not. So discretization error is the error using due to the numerical solution of partial differential equation, and it include error due to numerical approximation of governing equation and the boundary conditions. So yes, discretization here, the discretization means domain. I was talking about the domain, but here not domain. Discretization of equations. This is your governing equation and the boundary conditions. Obviously, your mesh is also involved. Discretization means both the mesh and the equation we are talking. So remember. So convergence is defined for elimination method, iterative solver, discrete solver, or the Kerber solver. So which option will be correct? Option A will be, that is elimination method. The convergence is defined for elimination method, not your iterative method, direct method, or not for the Kerber method. So the convergence is a property of iterative solver used for solving the discretized system of equation. It cannot be defined for direct solver as they do not have repeat step and similar answers. So okay, so we have completed today. We have completed around 34 questions. So we'll meet again on the next Sunday, that is 12. So anyone, anything? If not, so we can close. Okay, so thank you. Thank you, Deep. So thank you all. Now you can leave the class. No issue.